let's go to the previous part very quickly. Okay? Kind of quick review. Okay, in this chapter, consider the Fourier transform. Actually, that can be considered as an extreme case of Fourier series transformation. Okay, so suppose I have remember that in the Fourier series expansion, suppose I have a periodic function, let me call it x delta of t. So suppose this is a periodic function. Okay, so this is x delta of t. The period, fundamental period is t sub 0. So t sub 0 is the fundamental period. Then from the Fourier series expansion, we know the periodic function can be written as a summation, as a sum of the complex exponential functions. So actually cosine, sine, sinusoidal functions actually. Okay, summation xn e to the jn omega sub 0 times t. This omega sub 0, that is the fundamental frequencies, we call that, okay, which is given by 2 pi over t sub 0. And the t sub 0 is the fundamental period of the function. Okay, and the coefficient x sub n, actually that's a projection. Projection of the function x delta of t onto the complex exponential function. But careful here, there's a negative sign, minus sign here, because we use the complex conjugate of this exponential function to determine the coefficient. Okay, so it's kind of average value of x delta of t times this complex exponential function in the interval from negative 1/2 t sub 0 to positive 1/2 t sub 0. Sometimes it also can be written as from 0 to t sub 0. It's up to you, it doesn't matter. Now, if we imagine that if we let this periodic function, okay, the period of this periodic function be extended, okay, this t sub 0 be extended to a big number, become larger and larger and larger. Okay? So, let me zoom in a little bit. So this function eventually can be extended to from negative infinity to positive infinity. Okay? Again, we let the period t sub 0 be a big number. Okay? Now bigger and bigger and bigger and bigger. So this function eventually being extended from negative infinity to positive infinity. And that is the way we consider a non-periodic function. Okay, so let me repeat that again. The Fourier series expansion initially is for periodic function. Periodic function. The period is t sub 0. So that we have a Fourier series expansion. Okay, so Fourier series expansion, basic assumption is the function is a periodic function, and the period is t sub 0. Now, what if we are dealing with a non-periodic, or sometimes we call it aperiodic, okay? Non-periodic or aperiodic, okay? Aperiodic. Which means it is not periodic. And how do I implement the result of Fourier series expansion to that aperiodic function or non-periodic function? A very simple way, okay, kind of tricky. We extend the period to infinity. That's it. That's basically the idea. Okay? And then when we extend the period to infinity, in the meantime, we also redefine the coefficient x sub n. If you look at the Fourier series expansion one more time, this periodic function can be written as the summation x sub n, the coefficient, times the sinusoidal function or complex exponential function. Okay? And this x sub n can be determined by the projection of the function onto the sinusoidal function or the complex exponential function. Now, since we extend the t sub 0 to infinity, so if we don't make some multiplication, we have a problem here. Okay, so we define a function, we call it x of omega n equals the t sub 0, the period, t sub 0, times xn, xn is this one. Okay, that is the definition we made for coefficient. And then we define omega n as n times omega sub 0. This omega sub 0, that is the fundamental frequency. Okay, and then the frequency initially is discrete frequencies. Zero, 1 omega 0, capital omega. 2 omega 0, 3 omega 0, and so on and so forth. Okay? And you can see that this omega 0 is 2 pi over t sub 0. Okay? And the distance between the two discrete frequencies is, let me call it delta omega 0. That is actually omega 0. That is the distance between two discrete frequencies. Okay? So we'll keep that in mind first. And what we're going to do now is to let this period be a huge number, big number, okay? So this is 2 pi over t sub 0. Now, if this t sub 0 goes to a very, very large number, then you can imagine that the distance between the two frequencies becomes smaller, 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 smaller. So eventually, those frequencies will be very close to each other, becomes a continuous distribution. Continuous distribution. Okay? Oops, sorry. So in this case, the Fourier series expansion now can be replaced by the following definition. Okay? This is x of n. Okay, and omega n is n times omega sub 0. Yeah. Okay. Alright, so this is t sub 0 now is replaced by, look at this one. Okay, so t sub 0 is replaced by delta omega over 2 pi. So that's why we have this term. This one. Now it's replaced by 2 delta omega over 2 pi. Okay? And then we let the period, fundamental period, go to a very huge number. Then the difference, delta omega becomes differential, d omega. And omega n now becomes the continuous distribution omega. Okay, originally there's a gap between two different discrete frequencies. And now the gap becomes very, very, very teeny tiny small. So actually we are dealing with a continuous distribution frequency. So in this case, then this dimension now can be replaced by anyone. Okay? And then this delta omega now is replaced by d omega. Okay, and move the 1 over 2 pi to the beginning of the expression. And then the frequency response, x of omega, now will be given by this expression here. Okay, take a look here. Now the t sub 0 now goes to infinity. Goes to infinity. So that the upper limit of integration becomes positive infinity. and the lower limit of integration becomes negative infinity. Okay, and that's it. And omega n now can be replaced by simply use omega. We don't need to carry the subscript n anymore. So this becomes the Fourier transform. Okay, so briefly, let me say that one more time. When the function itself is a periodic function, then we can write the periodic function in terms of the sinusoidal function. And this is called the Fourier series expansion. This is only for periodic function. One more time, this is very important. While we are dealing with non-periodic function or aperiodic function, then we have to use the Fourier transform. So Fourier transform actually is dealing with non-periodic function. Okay, the period becomes positive infinity to negative infinity. So this is for a general function, okay? And the Fourier series expansion is this periodic function, right? So that's the start of Fourier transform. Okay. So this is the conceptual figure. So if we are dealing with a periodic function, and then the period, let me call it t sub 0. For this one, that's 2 seconds. And t sub 0 is 2 seconds for the bigger number 1. If you find the Fourier series expansion, you have the x of k, those are coefficients. Okay? And those frequency response, they are at discrete frequencies. 1 omega 0, 2 omega 0, 3 omega 0, and so on and so on. But once your period becomes larger and larger, bigger and bigger, you can see that the gap between discrete frequencies becomes smaller and smaller. It becomes smaller and smaller. This is for t sub 0 equals 5. This is for t sub 0 equals 10. Okay, so you can see that the gap between two discrete frequencies is very small now. But you can also increase this to, say, infinity. Then you have a continuous distribution of the frequency response. And in the meantime, actually your function, the function you are dealing with, becomes a non-periodic function or aperiodic function. Okay? This is a periodic function with period 2 seconds. And then you can see that this is only square in the interval, nothing else. So this is aperiodic function or non-periodic function. Okay? Question? Okay. Okay, now in order to be doable, in order to have the frequency response, x over omega, we have a condition for that. That is, since the frequency response is given by, if we go back to the, okay, the frequency response is given by the projection of the function based on t onto the complex exponential function or sinusoidal function, right? So in order to have this Fourier series expansion, Fourier series response, Fourier transform response to x of omega. And if I take the absolute value, then gives us the condition that we need. That means in order to have the Fourier transform, the function must be absolutely integrable. That means the absolute value of the function must be integrable. That means the integration of this function with absolute value functions is finite. Okay? That is the condition to guarantee the solution exists for the Fourier transform. Okay, but then we also can use the Laplace transform we have done before to find the Fourier transform. But under one condition, if, okay, this is very important, if the region of convergence of x of s contains the j omega axis. Okay? If this is true, then the Fourier transform of the function can be simply done by replacing the argument as in the Laplace transform by j omega, by j times omega. Okay? Because in this case, if you replace s by j omega, you have in the Laplace transform, you have this expression, which is exactly the Fourier transform of x of t. Okay, but again, the region of convergence must contain the j omega axis. Okay, so this is going to be tricky here. So in the next example, let me show this figure. I like this very much. Okay, Fourier series. Again, go back to the Fourier series expansion. This one. What's the meaning of this? Linear distribution. If you have a function, if this function is periodic, then the Fourier series expansion tells us this function can be decomposed as many sinusoidal waves, combination of many sinusoidal waves. Okay? So this is first mode, second mode, first component, let me say that. First component, second component, third component, and so on and so on. Now, if this is a periodic function, then this distribution becomes continuous. The distribution, the omega, becomes a continuous function. Okay, that's a very good figure to illustrate the Fourier series expansion and also Fourier transform. Okay, let's go to the example again. Now, in this example, I think I didn't tell you the complete story here. Maybe there's a misunderstanding here. And answer that again. Now, if I want to determine, or if we want to determine the Fourier transform of the unit step function u of t, this is u of t, this is u of t, then there's a problem here, there's a catch here. If we derive the Laplace transform of unit step function, we know it is equal to 1 over s, right? 1 over s is the Laplace transform of unit step function. Okay? However, this 1 over s actually comes from the condition. The region of convergence is this one. The real part of s. The real part, suppose s equals to sigma plus j times omega. Okay? The sigma must be positive. Strictly positive, does not contain zero. No equal sign here. Okay? So the region of convergence, ROC, is s equals sigma plus j omega. But the sigma is positive. Omega can be whatever the number is. So it does not contain the j omega axis. So that's a catch. So in this case, we cannot apply this result correctly. This result tells us if the region of convergence, contains the j omega axis, then we can use the Laplace transform. Replace the argument s by j omega, and we have the Fourier transform right away. Okay, but in this case, the region of convergence does not contain the j omega axis. In this case, if this is S plane, this is the real part, real axis, and here is the imaginary axis. For the unit step, the region of convergence actually does not include the j omega axis. It is the left half plane, entire left half plane, without the j omega axis. Okay? So if you replace the S by J omega, okay, let me say that. If you replace S by J omega, you have 1 over J omega, right? But this is not the Fourier transform of a unit step function, unfortunately. Why? Because the original convergence for this Laplace transform of the unit step function does not include the J omega axis, which violates the condition we need. Okay, and actually, if you look at the table, you will find that the Fourier transform of unit step function equals 2 terms, the sum of 2 terms, in addition to 1 over J omega. This one, there's another term, pi times the impulse response. Okay, that's a tricky part. And the way to find that is to rewrite this function, unit step function, as the sum. Okay, we use this one here. 1/2 times 1 plus signal of t. Sine function is signal. I think I have another figure here. This one. So this is the sine function. We call that signal function. Okay, when t is negative, then the function value is negative, -1 or negative. When t is positive, the function value is 1, positive 1. When t is 0, the function value is 0. Okay? So by rewriting the unit step function as the sum of constant value 1 plus signal function, and then divided by 2 times 1/2. Okay, we use this to express the unit step function. Okay, that's a little tricky. But by doing so, actually we introduce one more point here. We change a little bit. The function value at t equals 0, not 1/2, not 0. Okay? Originally, unit step function. For unit step function, t is 0. The function value should be 1. But now we modify that a little bit. Again, mathematics. Oh, okay, but let's change it now. Change it quite a lot. Okay, so now if we take the Fourier transform of the constant value 1 and also the signal function sine of t, we have 2 terms. For the constant value, the Fourier transform of 1 is equal to 2 pi times the delta function. And for the signal function, the Fourier transform is 2 over J omega. 2 over J omega. Here I attach the proof. Okay, I attach a proof here. Maybe you can take a look. To prove the Fourier transform of the signal function, okay, it's a little bit tricky here. We use a very interesting function to approximate the signal function. I don't know who figured this out initially. Okay, originally this is the signal function. Function value equals 1 when an argument t is positive. Function value equals negative when the function value when the argument t is negative. Function value equals 0 when t is 0. Okay? Now, instead of using this function directly, we modify that function by this e to the negative at times the unit step function of t minus e to the at times another unit step function of negative t. Now, if we try to sketch the function, okay, we call this as a of t. You can see it's very interesting here. Okay, when t is 1, This is f of A of t. When t is 1/2, this is the function. So when the parameter A becomes smaller and smaller and smaller, you can see this function approaches the second function more and more and more, right? So that's a tricky part. So we use f of A of t to determine the Fourier transform first. So we find the Fourier transform of this of A of t first. Okay? And then we have the f of A of t equals this. And then we take the limiting process. We let the parameter A approach 0. Then we have the Fourier transform out. So the second function, if you take the Fourier transform of the second function, then it equals to 2 over j omega. And here the 2 pi f, the f is the frequency in hertz. So 2 pi f here, that is the omega. Okay? And this is the way we determine the Fourier transform of the second function. I prefer to use this one. There are some other methods, but this one I think much more easy to understand. Okay? All right. And also we have another term, the Fourier transform of the constant 1. What is that? How do we find that? Well, y is equal to 2 pi times 2. Okay, there's another. So for the constant value function, okay, here x means t. Okay, so this is f of t equals 1. And then we are going to prove that the Fourier transform of this function is built out of s, or built out of t. Again, the way to prove it, okay, the function value we are going to prove is, we are going to derive is the Fourier transform of 1. Okay, the way we derive this is to express this complex exponential function as the combination of cosine function and the sine function, okay? By using the Euler's formula. So e to the negative 2 pi, I is j, okay? I becomes j, okay? So negative 1 e to the negative 2 pi j times x. X is t actually. Now can be replaced by cosine of 2 pi t. Oops, sorry. Hold on. Sorry, maybe. Okay, well, let's just do the definition here. Now, since you use 2 pi, so this makes the x becomes the frequency in terms of hertz. So that's why there's no 2 pi. But here we use percentage. And here we use radian per second, so we have 1/200 in front of the radian. It doesn't matter. Okay, the key point is you expand you use the Euler's theorem, Euler's formula, Euler's theorem, to represent the complex exponential function. Okay, and then you integrate this function. Now here's the tricky part. When you integrate the function, you use the limit in a sign, but be careful here. The upper limit and the lower limit, they are symmetric. Okay? The upper limit is gamma. The lower limit is negative gamma. So they are symmetric. That's a tricky part. If they are not symmetric, you have a problem. Since they are symmetric, so this term disappears eventually. Okay? Only one term left. And similarly for the second term. This is for the medical reason. Okay? If you don't use this symmetric limit, then we have a problem. Okay, and then let's proceed. One second. Okay, so if we integrate this, this is skew symmetric, so this can disappear. Okay, due to the upper limit and lower limit we are using here. We assume that gamma is the upper limit, negative gamma is the lower limit, and let gamma be a huge number. So this second integral, the integral of sine function is gone, is zero, because sine function is a skew symmetric function, so the integral is zero. Okay, so what's left? It's only the first term. The integral of this cosine function. Cosine function is symmetric. Symmetric. Okay, so we have two terms. Two of this. Become two of this. And limit. Gamma approaches infinity. 2 times sine 2 pi s over gamma. And that is the frequency in our notation. Okay, and instead we replace the gamma by 1 over epsilon. And let epsilon be a small number. Okay, and then there's the expression. This expression. This expression here eventually equals the delta function we define. So this method to prove the retracement of the constant function 1 is a little tricky, but I think this is much more easier to understand. We take the limiting process, okay, and use here. And use a very, I don't know how to say that, very clever, maybe use the word clever method to assume the upper limit, the lower limit are symmetric. Okay? If they are not symmetric, we can know this kind of conclusion as well. Okay? All right, so now we have shown you that the Fourier transform of the constant value 1 is equal to the delta function. Okay? And actually, if you use our notation, there's another 1 over pi in front of it. Okay, so let's go back to the previous page. Okay, so that's why if we derive a Fourier transform of unit step function, we have the sum of the two terms. One is from the secant function. Yeah. This is from secant function. And this one is from the constant function form. Okay? All right. Okay, so let's move on to the next example here. Now, what if the original convergence does include the geometric axis like this example here? Suppose the function we are going to derive is e to the negative 2t times the unit step function. And the Laplace transform of this function is given by 1 over s plus 2. And we can derive the original convergence. Okay? I think that's very easy to see that. Is if s, again, s is bigger than negative 2 in this case, in order to have this Laplace transform. Okay? So which include the geometric axis. Negative 1, negative 2. This is real part. And this is imaginary part. So here, the entire half plane to the right of negative 2, they are the original convergence. Okay, our C original convergence rule 1 over s plus 2. So which means it includes, it contains this geometric axis. Okay? So now we can replace s by geometry to obtain the Fourier transform. To obtain the Fourier transform of this to x to t directly. Okay, that's the easy one. And similarly for the 3, the same. For this one, the Laplace transform is given by this. And the important thing is the original convergence is in a strip between negative 1 and 1. Okay? You can derive it by yourself, and we just give you the result directly. So this case, negative 1 and 1. And this is 10. So in this case, this strip is the original convergence. This is the original convergence, obviously. So again, it contains the geometric axis. So we can replace, to determine the Fourier transform of the function x3 of t, we can simply replace this by geometry. And that will give us the Fourier transform. Or call this, I prefer to call it frequency response. Okay, directly. 2 over 1 plus omega squared. Okay, so that's the benefit of using the Laplace transform if the original convergence contains geometric axis. Okay, all right.
Okay, let's move on to the next one.
Right, one more time, the Fourier transform is a linear function. The way to prove it is straightforward. Suppose we have two functions. One is x of t, the second function is v of t, and the Fourier transform of x of t is capital X of omega. Okay, and capital V of omega is the Fourier transform of v of t. So we are going to show you that if I have a linear combination of x of t and v of t, and then the Fourier transform of that function is also a linear combination of x of omega and v of omega. Okay, so the proof is straightforward. We replace, let's assume, and we use this word. Let's assume 12 of t is the linear combination of x of t and v of t. So I plug it into the definition for Fourier transform. So this is the definition for the Fourier transform. Okay? And replace 12 t by a times x of t plus b times v of t. And then I can split this integral into two terms. Again, a catch here. We have to assume when you are dealing with this, when you try to split the function into two terms, we have to make sure that these two functions, they are finite. Okay, that's a problem. If you don't have finite function, you have a problem. Okay, so careful. Now, let's assume that it doesn't happen here. We are dealing with the good functions. Okay, so we can split the two terms. And then the first term, actually that is the Fourier transform of x of t times the parameter times the coefficient a. And then the second term, that is the Fourier transform of the v of t and then times the parameter b. Okay, so that's easy to prove the linearity. Okay, and then the second property is inverse proportionality of time and frequency here. Suppose we have the function x of t initially, and we know the x of omega, capital X of omega, is the Fourier transform of x of t or the frequency response of x of t. Now, if we multiply the function value, I mean the argument t, by a scalar model, how do I get rid of this here? Can I get rid of this? Does anyone know how to get rid of this? Here. This way here. Okay, one more time. Okay, now if the argument t is multiplied by alpha, okay, that means we either stretch the function or compress the function. Okay, if alpha is bigger than 1, then we compress the function. If alpha is smaller than 1, we expand the function. Okay, look at this. Then what will happen? Then the corresponding Fourier transform will also be either stretched or compressed, either stretched or compressed. Okay, let's take a look at one example. Okay, suppose we have x1 of t, a rectangular function, and this is the Fourier transform of x1 of t. Okay? Now, if I multiply the x1 of t by, the argument t by 1/4, so t becomes 1/4 of 1/4 times t. So which means we stretch the function, the function becomes wider. Right, becomes wider. Then you can see that the corresponding Fourier transform becomes much more concentrated at the zero, becomes compressed. Okay? You stretch the function in the time domain, then you compress the Fourier transform in the frequency domain. That's for alpha equals 1/4. Alternatively, alternatively, if we compress the function look at this figure here. Originally, we had the blue line, the x of t, and the corresponding Fourier transform is this one. Okay, this one. This is the Fourier transform of the x of t of the blue line. But now, if we compress the function, so if we have the red one, this one, okay, the function becomes narrow, becomes compressed. Okay? Then the corresponding Fourier transform becomes this one, with the red one. So in the frequency domain, the response is stretched. Okay? So we have a very interesting phenomenon here. If you compress the function, like in this example, if you compress this function in the time domain, you expand the function in the frequency domain. Alternatively, if you expand the function in the time domain, you compress the function in the frequency domain. This is reasonable. Why? Because if you look at this function, if you look at this function, this is much more like a constant function, right? Much more like a constant function. For a constant function, the major component is low frequency component. So most of the frequency response concentrate on the low frequency range. Okay, that's reasonable. That is reasonable. Okay, makes sense. All right, let's take a break and then come back after the break. Okay. All right, the next important property we are going to consider is the duality here. Now, if we have a function x of t, the corresponding Fourier transform is x of omega. Okay? Now, if I use this function x, capital X, that replace the argument by t, okay, look at the form. We use the function of the Fourier transform, but replace the frequency argument by the t, the time domain t, and then take the Fourier transform. Then we will find that the corresponding Fourier transform becomes 2 pi times x of negative omega. Now this x, that is the original function x of t, but with the argument negative omega. Quite interesting. The way to prove it quite straightforward. Take a look here. So initially we have the function x of t, and then we take the Fourier transform. So this is the Fourier transform of x of t. The integral of x of t times e to the negative j omega t, and then dt. Okay, again, this is a projection. Actually, it's a projection of x of t onto the sinusoidal function. All right. And then also we can rewrite the function x of t as the integral of x of omega times e to the j omega t to omega, and multiplied by the parameter 1 over 2 pi. Oh, by the way, I have to tell you that if you look at some other books, they may give you slightly different definition of the Fourier transform. Some of the book, they may use 1 over square root of 2 pi in front of this integral. And then in that case, the associated x of t becomes 1 over the square root of 2 pi squared, and then times the integral. Why they do that? Because in this case, then the expression becomes symmetric or identical. Okay, one more time. Some of the other book, the author define the Fourier transform as 1 over the square root of 2 pi. Okay, they put the parameter 1 over the square root of 2 pi in front of this integral. In this case, the corresponding inverse Fourier transform for x of t is 1 over the square root of 2 pi and then times the integral. Okay, that also possible because just a definition doesn't make sense. Okay, but what if we replace the argument t by negative. Okay, now if we replace the argument, this argument t by negative omega, just an argument, so I can replace it, and multiply by 2 pi. So this 2 pi now is multiplied to x of t, and then replace the argument by negative omega. Okay? So this t over here, this t over here, this now is replaced by negative omega. Negative omega. Okay? But then the argument, okay, is a dummy variable. So I can call it whatever I want. So let's define it as small rho here. Small rho here. Okay, so this argument, this dummy variable omega, this dummy variable omega now is replaced by rho. Replaced by rho here. Okay? So one more time, we replace this independent variable t by negative omega. This one? I cannot see it. Okay, replace. Replace t by negative omega. So here the t, this now is replaced by negative omega, right? And then the dummy variable, this omega, this omega, this omega. This one here. Now it's replaced by rho, and this rho over here. And also rho. Doesn't matter. It's just a dummy variable. Okay? And then also I can call it, say, t eventually. Actually, you can use t here eventually. So this rho now is replaced by t. Rho is replaced by t. So once you have the t as the dummy variable, then this is simply the Fourier transform of capital X of t. Capital X of t. So this is the duality of the Fourier transform. Very, very interesting. Now one simple result, but also very important is, okay, we have shown this one. If we take the Fourier transform of this build-up function, then the associated Fourier transform is 1. It's 1. Here is the pencil here. Okay, so actually that's 1. So the Fourier transform of the delta function is 1. Okay? So now if we take the Fourier transform of this function and multiply by a constant, if we take the Fourier transform of this constant a, that will give us 2 pi times x of negative omega, okay? Which is delta of negative omega. But this delta of negative omega is also equal to delta omega because it is symmetric. It is symmetric. It is right at the center, so it doesn't matter. It does not change anything here. Okay, so that's the duality of the Fourier transform. Okay, there is another quick example here. If we take the Fourier transform of the delta function delta of t minus rho sub 0, okay, rho sub 0 is a shift in time domain, plus delta of t plus rho sub 0. Okay, so one is delay minus advance. Then the associated Fourier transform is equal to 1 times this is the time delay in the frequency domain, okay? Without initiate that directly. Suppose I have a function x of t, and then the associated Fourier transform is x of omega, capital X of omega. Now if I define another function of t equals x of t minus t, so it's the time delay. So suppose I have a x of t like this, for example, and then the y of t will be c seconds delay. So it will be c seconds delay. C seconds delay. Okay, now if you take the Fourier transform of this y of t, then it is equal to the x of omega times the delay in the frequency domain. Because if you look at the Fourier transform, this is much more easier to remember. In the Fourier transform, if I take the Laplace transform, in the Laplace transform, excuse me. In the Laplace transform, if we take Laplace transform of this delay function, half seconds delay, then the Laplace transform is equal to f of s. The Laplace transform of f of t multiplied by e to the negative half s. Okay, so this by e to the negative half s is the operator of time delay, but in the s domain, in the frequency domain. Okay, so you multiply the f of s by e to the negative half s. Alpha is the delay time. Alpha is the delay time. Okay, so in this case, the j omega is actually the variable is in the Laplace transform. And c, that is the time delay, okay, c seconds. Okay, let's go back to the example here. So in this case, we have a rho sub 0 seconds delay. So this is the delay time. And j omega, like I said, that's in the s domain, that is s. Okay, but in the frequency domain, we replace s by j omega. Alright, so the Laplace transform of the delta function with rho sub 0 seconds delay is given by e to the negative j omega times rho sub 0 that we produced that. Okay, and likewise the Fourier transform of the impulse response with negative rho sub 0 advance and equal advance will be this rho sub 0 as a time advance. And then multiplied by j omega. Okay? So this function is the operator in the operator of time delay or time advance in the frequency domain. The sum of these two terms is equal to the cosine function. So alternatively, if you use this cosine function as the time function, okay? And then take the Fourier transform of this time. That will give you the associated Fourier transform, which is the sum of two delta functions, okay? And multiplied by 2 pi again. So that's a duality, which is very useful. All right. Okay. Let's move on to the next one. Speed up a little bit, sorry. So here is the example given by the book directly. So suppose we are given the function x1 of t, is a rectangular function. And this is the associated Fourier transform. Okay, kind of single function. The single function is this INC single function, kind of single. Now if we switch, okay, if we move the single function to the time domain, and then take the Fourier transform of this function, then that will give us a rectangular function, but in a frequency domain. So this is the duality of the function. Okay, one more time. This function is in the time domain. Okay, and after taking the Fourier transform, we have a single function in a frequency domain. But now if you use the single function plus the time function, and then take the Fourier transform, you can see that the associated Fourier transform recovers this rectangular function. Okay, quite interesting. That's mathematics, very useful. Okay. Well, any question up to this moment? Sorry, I moved very fast. Okay, because some of the stuff we have gone through one time. Okay, so I have to speed up a little bit. Any question up to this moment? Okay, all right. If you have a question, then you can stop me, okay? Raise your hands. Stop. Okay, now here we are going to reconsider the modulation or frequency shift. We have this one before. Actually, in the Fourier series expansion, we also have this one. Okay, but in the Fourier transform, we have a similar result. So let's consider the function x of t. Suppose we have a function x of t, and the associated frequency response of Fourier transform is capital X of omega. Now, if I multiply this x of t by the complex exponential function or sinusoidal function e to the j omega 0 times t, then in the frequency domain, we shift the spectrum omega sub 0 radian per second. So if you multiply the time function by a sinusoidal wave, this is actually a sinusoidal wave, with the frequency omega sub 0, then in the frequency domain, we shift the power spectrum, omega sub 0 radian per second. Okay? And how do we prove it? Kind of straightforward. Again, so let's take the Fourier transform of this modulated signal, x of t times this exponential function, complex exponential function. Okay, so by definition, we integrate this function. The original function is times e to j omega sub 0 t, and then times the exponential function e to the negative j omega t. Again, this is the projection. Okay, this integral of two functions, the product of two functions means the projection. Okay? We want to see this function on the component of this function on this direction. Okay? Alright, so we can collect the two omegas in the complex exponential function. So by definition of the Fourier transform, this integral actually has the Fourier transform of x of t with the frequency omega minus omega sub 0. Okay? So take a look. Here is one example. So originally I have a function x1 of t. Okay? So this is the function. Okay, we call this the message. The message to be modulated. But then we multiply this message by the carrier e to the j omega 0 t. So we have a modulated signal like this. We have multiplied it by cosine omega sub 0 t actually. This function. So this is this one. Okay? We multiply x of t by the cosine function. Cosine of omega sub 0 times 2. And then if we look at the frequency response, this one is the frequency response of x1 of t. Okay, the original message x1 of t. This is the frequency response. Okay, but we can see only the magnitude, so here is the magnitude. It's fine. Now, if we take the Fourier transform of this modulated signal, we will see two components. One is at 10 radian per second. Okay, what does that mean? Because, the omega sub 0 we are using to modulate the signal is omega sub 0 in this case is 10 radian per second. Okay, look at this function. 10 radian per second. So we have one component at 10 per second. 10 radian per second. 10 radian per second. Another one is at negative 10 radian per second. And how come? Because this cosine function we multiply to the original signal, okay? Cosine omega sub 0 t omega sub 0 10 radian per second. Actually, it can be written as 0.5 times e to the j omega sub 0 t and 0.5 times e to the negative j omega sub 0 times t. Okay? And if you take the Fourier transform of this guy, it will give you, okay, again, go back to the, we've done this one. Yeah, okay, that's all. This will give you the frequency shift. One more time, go back to this. Okay, if you multiply the original signal x of t by e to the j omega sub 0 t, then in the frequency you will have a frequency shift. In the frequency domain you have a shift. Okay, the same omega sub 0 radian per second shift. So this will give you 10 radian per second shift. This one. Okay? This will give you this one. And then for the next e to the negative j omega sub 0 times t. And this will give you the negative 10 radian per second shift. So which will give you this one. So the first component shift to here. The second component, this is the second component. Now shift to here. Now the thing I want to remind you are the following. Number one, since you modulate the signal, okay, with the sinusoidal signal, the frequency is 10 radian per second. Once you modulate the signal, you split the frequency. Okay? And look at the magnitude here. The peak value here is about 2. This is 2, right? But once you split, you divide the power, you divide the energy into 2 parts. The maximum value, the peak value becomes 1. Be careful here. Because you split, you divide your signal into 2 parts. One is from the negative frequency, the other one is from the positive frequency. Okay? All right. Yes, that's the duality. I'm sorry, that's the frequency shift. Modulation. Okay, what about if we still want to take the Fourier transform of a periodic signal? In the beginning, we mentioned the Fourier transform is for a periodic or non-periodic signal, right? But what if we are still want to apply the technique to a periodic function, x of t? We still can do that because remember that the periodic signal x of t can be represented by using the Fourier series extension. Okay? So we take the Fourier transform of x of t, no matter what, by using the Fourier series extension. We still can do that. And then we have the Fourier transform x of omega equals to x of k. And this x of k, x of k times the Fourier transform of this exponential function e to the j k omega sub 0 times e. The Fourier transform of this guy is equal to 2 pi times the delta function with a frequency shift k omega sub 0 frequency shift. Okay? And that's the previous power, right? So this is the way we deal with periodic signal. One more time. The Fourier transform is for non-periodic signal or aperiodic signal. Okay? But if we want to take the Fourier transform of a periodic signal, what can we do? What can we do that? The answer is yes. We still can do that. We can do that by using the Fourier series extension of a periodic signal. And then take the Fourier transform of a complex exponential function. And then sum up all the terms if you want. Okay? So this is the way we deal with periodic signal. Okay? So here's a quick example here. Suppose we have a periodic signal. And in each period, the function is given by the combination of 3 random signals. So here is the signal. So in each period, this summation of the 3 random signal gives this triangle function. Okay, give this triangle function. All right. So now if I implement the previous result, so I have to find what are the corresponding coefficients x of k first. So the Fourier coefficients x of k by our previous analysis of our previous methods is given by 1 over t sub 0. This is the coefficient. Kind of we are doing a mean value, right? And times the Fourier transform of this function, x1 of x. And replace s by j times 2 pi times k. Why it is 2 pi? Because the omega sub 0 is 2 pi. Fundamental frequency is 2 pi. So this is fundamental frequency. Okay? And we have done this in the previous example, so maybe use the result of that. And also the x of 0, which is the mean value. Okay, like I asked you the question last time. X of 0 of the Fourier series expansion, the first term, actually that is the mean value of the function in the interval. So now if we look at this interval from 0 to 1, the mean value of this triangle is 0.5. It is 0.5. So from the figure, we can see that very clearly. But also we can compute that analytically. Okay? Alright, so we have the stuff we need. Here we have x of 0. And we have x of k. So we can plug into the Fourier transform expression and then sum up. Now, theoretically, we need infinite terms. We need infinite terms, but practically we don't do that. We use only maybe up to 10 or 20 terms, but depends on the function we are dealing with. Now, since this is one more example of dimension here. This function, this triangle function, you can see that it is continuous. It is continuous. But if you take the differentiation, take the derivative, the first order derivative is not continuous. This is x of t. Now, if you differentiate this function, okay, positive, negative, positive, negative. This is x dot of t. The first order derivative becomes discontinuous. So, which means the coefficient will be 1 over k squared. And the conversion rate is very fast. For this case, we need about maybe 3 or 5 turns, or less than 10 turns. It will approximate this function very well, okay? Because this is k squared. It converges very fast. We need only a few finite terms. Then the Fourier series extension will approximate the function very, very well, okay? So that's something I have to remind you. Okay, let me skip this one for a moment. Pascal's here. Let me skip that for a moment. Okay, we have a little bit trouble here last time, so let me refresh that memory a little bit. This is talking about the symmetry of spectral representations, symmetry of Fourier transform, Fourier series, excuse me. Now, if we consider a real value signal, x of t, which is the real value, okay? Then we have the following result. The corresponding Fourier transform or Fourier response can be written as the real part and the imaginary part, right? In this case, for a real value signal, then the real part is symmetric. I'm sorry, or even. We call this even, symmetric or even. And for the imaginary part, it is skew symmetric or odd function. Graphically, I prefer to use this one. Okay, suppose we are considering a complex plane. If this is x of omega in a complex plane, x of omega, it is real part and imaginary part. So this is imaginary part, and this is the real part. Okay? Now, we try now, so now we are going to prove that or show that the complex conjugate of x of omega actually equals to x of negative omega. So graphically means that this x of omega actually is the complex conjugate of x of omega. So they share the same real part. They share the same real part, but the imaginary part, the different part is sign. Okay? How come? Okay, again, start from here. Okay, I prefer to use this one proof. Maybe this is easier to prove that. The Fourier transform of x of t by definition is equal to the integral of x of t times this complex exponential function. And then we rewrite, this complex exponential function is cosine function and the sine function. Cosine of omega t minus j times sine omega t, right? Okay, so now if we change change the sign of the omega. We change the sign. So we have x of negative omega. You see what happens? Now the Fourier transform x of negative omega, by definition, we replace this omega by negative omega. So the minus sign will disappear. And then we can rewrite this complex exponential function using Euler's formula. So we have x of t times the sine of omega t plus j times sine of omega t. Now compare with x of omega, compare with this one. You can see that the real part are the same. The imaginary part differ by the sign. Okay? And this is indeed the complex conjugate of this x of omega. Okay, so we have just proved the complex conjugate of x of omega actually equals to x of negative omega. Okay? So that's why I can show you by using this figure. And then from this figure you can see that the real part of x of omega and x of negative omega are the same. This is the real part. And the imaginary part, they differ by the sign. This is the imaginary part of x of omega. And then this is the imaginary part of x of negative omega. Okay? Alright. Now if we go back to the previous proof, I think the thing I missed is, here I replace the omega by negative omega. Negative omega prime is fine. And then, here. Then in this case, originally I go to here. Multiply by 1 over 2 pi. Then I have to change the lower limit and upper limit, so this becomes negative omega, and this becomes negative omega. But in the meantime, the d omega becomes negative d omega prime. Okay, that's something I missed last time. Okay, and then bring this up. So now, if I switch the upper limit and lower limit, I switch the upper limit and the lower limit. I also have to replace the sign, replace the negative sign by positive sign. And I will go back to this expression. Okay, but I think the way that I showed it today, I think it's a little bit easier to understand because with this one. Okay, so I prefer to use this one. Okay? Alright, those kind of stuff, kind of boring, but you have to know that, sorry. Bear with me, bear with me. Okay, so here is a quick example. For the function x, for the function x1, is a unit step of u of t minus s, which is the potential function. This is the function. Okay? And then if we take the Fourier transform, you can see that the magnitude of the function is even function. And the argument is an odd function. This is an odd function. Okay? The magnitude is even function. The magnitude. This is the magnitude. This is the magnitude. It is symmetric. For positive omega and negative omega, they are the same. Okay? But if you look at the argument, for x of omega, this argument suppose is positive, then the associated complex conjugate function for x of negative omega will be negative argument. Okay? So if we consider the argument, then we have to change the sign. It becomes a whole function. So you can see that. Okay? So the argument, this is the argument of the Fourier transform, now is the whole function. And similarly, we consider another function, exponential decay function. This one, the Fourier transform, and the magnitude of the Fourier transform is also even function again. Is even function, symmetric function. If we look at the argument, it is also an odd function, Okay? So this convinces ourselves that the derivation, the result is not correct. Okay? Which one is with this? Nothing here. Windowing, this is important. For signal process, if you try to process a signal, usually we have to add a window to the signal. How come? Because, in many of the cases, the edge of the signal usually has a kind of whatever disturbance. And we try to attenuate or we try to minimize that disturbance. Okay, so we multiply this original signal by a window. This is a window. This is a window. And hopefully, after multiplying the window, the signal, this one, will have a better frequency response in some sense. Okay, look at this. This is the signal recorded from a sensor, whatever the signal is. And then we have the frequency response. Okay, these are we call this leakage. This is the major component of the signal. And this is the secondary component. These small ripples, they are the leakage. Okay? They are not supposed to be there originally for some reason, if I know that, okay? And then how do I get rid of this? We multiply the signal by a window. Here we use any window. So after multiplying the window, this edge now kind of minimized, sort of. If you look at the Fourier transform of this signal, this is the frequency response. Compared with this one, you can see that the ripple now almost knocked down. Right? Okay? So this is a very useful technique to minimize the disturbances that you don't want, especially at the edges of the signal. Okay? And the theoretical background comes from here. Suppose I have a signal, x of t, and I want to multiply the x of t by a window function. Let me put w of t. So the Fourier transform of this windowed signal, and then put windowed signal. Well, t will be given by this one. The well t is given by x of t times, this is x of t times w of t, right? Okay? So, and then this w of t can be moved into the integration. This is independent variables t. So we can move w of t into the integration. And then take the Fourier transform. And you can see that this becomes the integral of x of rho, the dummy variable, times the Fourier transform of this. Okay, w of t times this exponential function. One more time, let me repeat that again. This is kind of crucial, but very important. Looks simple, but very important to say that. Y of t is equal to w of t times x of t. Okay? And then we can move w of t into the integration. Okay, so far so good. We didn't do anything, just move the function into the integral. And then we take the Fourier transform of y of t. So we take the Fourier transform of this. Okay? Now, just 1 or 2 bytes constant, so forget about that. The only term inside the interval involving the time is WLP and this exponential function. So we only have to take the product of these two functions. We take a Fourier transform of the product of these two functions because they are the only functions involve the t, involve the time. Okay? And this turns out to be the Fourier transform of W with the time shift, the frequency shift rho in a frequency domain shift. Okay? Rho. So indeed, while omega, the frequency response of y, the windowed signal, actually is a convolution of the frequency response of the original signal W and the windowed signal. Okay? So y was x times W. The Fourier transform will be equal to 1 over 2 pi times the convolution of S and W. X and W. Okay? Now, if you want to ask me, well, how do I choose the window function? Well, I don't know. I have to say that. By trial and error. By experience up to this moment. And there are many window functions we can choose. Okay, this is one of it. 1, 2, 3, 4, 5. Okay, a little bit more than that. Okay? And the right hand side, the blue one, they are the frequency response, the Fourier transform of the window function. These are not the only function you can choose. There are many window functions. They look similar. Kind of bell shape. Okay? But I have to show you that they are not the only function you can choose. I have some other functions. Hold on a second. Okay, I find it now.
Yeah, there are many out there. 1, 2,
3, 4. Okay, there are many. Okay, different parameters give you different function. Yeah, function. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And more. Quite a lot. Okay, so there are many functions you can choose. But again, if you ask me, how do I know which one is the best one? You have to try. Depend on your problems, depend on your signals. No kind of standard precision. But if you did it a lot, you will feel which is better. But again, I try the error. You will experience later on. Okay? All right, and then the filtering. Okay, what is a filter? Filter means suppose I need to get rid of some unwanted component of the signal. Then I have to use a filter. Suppose, look at this figure here. Suppose I have a signal, this one, which is a combination of 3 different components. One is low frequency. This is low frequency. Another one is high frequency. And this is the middle. Okay, the middle frequency. Let me say that. So now if I want to allow the low frequency to pass, and then try to get rid of the remaining 2 components, then I'm going to use a low pass filter. I'm supposed to use low pass filter. So So when I use this low pass filter and I let this signal go through this low pass filter, only the low frequency component will go through. The remaining two components will be attenuated. Okay, will be attenuated. Means they will become, the amplitude of the remaining two components becomes very small. Actually, we have seen this one before. We have seen the one with, where is that? In chapter 2, I think. First order system, okay? I also show you the function, beta function. Go back to look at the function. And this is the only part of frequency response of the low pass filter. We are, okay, this region corresponds to low frequency. And this region corresponds to middle frequency. And this region corresponds to high frequency, supposed in that sense. Okay? So now if I use a low pass filter, then only the low pass frequency component can pass. The other components will be attenuated. Alternatively, if I want to allow only the high frequency component to go through, to pass, then I choose a high pass filter. This is high pass filter. Okay, this is a high pass filter. Then the low frequency component and also mid frequency components, they are also attenuated. So only the high frequency component can go through. Now, if I want to allow only the middle frequency component to go through, and then get rid of the low frequency component, and also get rid of the high frequency component, then I should use the band pass filter. So this is the band pass filter frequency response. Only the frequency range in between will go through. Then the other low frequency and high frequency component will be attenuated. Okay? Now, alternatively, what about if I allow high frequency, this is low frequency, allow low frequency component to go through, allow high frequency component to go through, but I want to kill the middle one, okay? I don't want this middle one to go through. Then I should choose the band pass, or sometimes we call that loop. I should say last loop. Okay, one more time. If I only want the high frequency component to go through, and also this is low frequency component, and this is high frequency component to go through. I want to kill the middle one. Okay, this is middle frequency. Then I should use the notch filter. Notch filter, kind of hole. Okay. So in this case, only the middle one will be killed. Only the middle one, you can see the middle one disappeared, this one disappeared. Only the low frequency component goes through, pass through. And then high frequency component also pass through. The middle one is gone. The middle is gone because it's killed. So this kind of filter is called notch filter. Okay? So basically we have the following four types of filter: low pass, high pass, band pass, low pass, high pass, band pass, and also notch filter. Okay? And how to design the filter is a very interesting topic. Hopefully we have enough time to go through that. Okay? All right. Okay, by the way, sorry. I think I have here is a quick example. Suppose I have a signal, x of t, and this is the frequency response of x of t. And then this signal, x of t, will be disturbed by the signal. N of t, this is noise. Okay, this is noise. And the power spectrum or frequency response of the noise given by this one. So these are the frequency response of the noise. So the signal involving the XRT and the noise gives this power spectrum, gives us this frequency response. So now I want to get rid of this unwanted noise, okay, because they are noise at the moment. What should I do? I have to use a low pass filter. So this is the ideal low pass filter. So once I go through this ideal low pass filter, I have a very beautiful frequency component of the signal. But again, this is impossible. This is only for theory. Okay? Practically speaking, this is impossible. Because this signal, this filter, actually is the non-causal signal. You cannot do it real time. Okay, because this signal, this filter, this is a frequency response of the filter. If you go back to the time domain, take inverse Fourier transform, it will give you the time response or repulse response of the filter. And you can see that it is non-causal. Okay, this is for t greater than 0. This is for t smaller than 0. So that means this filter cannot be done in real time. It can only be done offline. So which means you are going to collect all the signals and then go through this non-causal signal. You can do that if you use the offline process. Okay? But if you do it in real time, you won't be able to implement this ideal filter. Okay, that's a problem. That is the problem. Okay, unfortunately, I think I have to stop here, otherwise we are going to lose our power back. Quite soon. So I have a homework assignment for you. Okay, number one. Number one, go to the method code, okay? For example, 5.19 over here. And this one. Okay, it's on page 356. Modify the code. Modify the code. Modify the code for example 5.19, okay? So that you can draw the Fourier plot or the frequency response or Fourier transform of the following four filters. Okay? Got it? Modify the code for example 5.19, 5.19, okay? 5.19. So that we can use the code after the modification to draw the frequency response of 1, 2, 3, 4 filters. Low pass, high pass, band pass, and band stop. That's the natural picture. Okay, there's an equal sign missing here. Okay, got it? Alright, any questions before we leave? Sorry, we have to speed up. Sorry about this. Any question? Okay. All right, then see you next week. Have a good weekend.